So the work that we do is positive on this, we're going up, and it gains some potential energy. The work that we do is equivalent to energy. We say the work of external, which is my hand on this, equals to change of its gravitational potential energy. And because the force that I'm applying upward is exactly opposite of the gravitational force, the work that the external force does, because we're going at equilibrium, is negative of work of the gravity itself. Negative of work of gravity. Remember, when we go up, the work of external force is mg delta y, and the work of the gravity itself is negative mg delta y. So these are opposite of each other, right? So if we say the work of external force is equal to change of potential energy, then in terms of work of gravity, change of potential energy, delta U of gravity is negative work of gravity. If you put work of gravity from this equation, the negative sign cancel each other. So delta U for gravity is equal to mg delta y. Mg, if I now write this delta y, that what this means mathematically means that you have that, right? So you can see that final is with y final, initial is with y initial. So in general, you can say gravitational potential energy is just mgy for any y value according to the coordinate system. Remember, the work that we talk about here for gravitational force, there is a y-axis that's always upward. Right? Y-axis should be upward for this to work. Because when you go up, the work of gravity is negative. If you go downward, work of gravity is positive. So this is according to y-axis that's upward. So if you have y-axis that's upward, you can say just gravitational potential energy is equal to mgy. So this, of course, that y depends on where you start y-axis. So you take y one level to be 0, you assign potential energy due to gravity 0 at that point. Then throughout the problem or throughout the experiment, y changes, the potential energy due to gravity changes. And because this is up to you, only the change in potential energy usually affects the problem, not the value at any point. All right, so this is how we get gravitational potential energy. The same thing if you just stretch a spring, the work that you do goes into potential energy of a spring. And work that you do is also opposite of the work that the spring does. So the potential energy the same way, change in potential energy of a spring is equal to W of external force. But W of external is opposite work of external force is equal to negative work of the spring itself. The work of a spring, remember, was negative 1/2 k x2 squared minus x1 squared. Change in potential energy of a spring is negative of the work of a spring, but work of a spring is negative of this or negative of that, so it becomes positive 1/2 k x final squared minus x initial squared. And that is us final minus us initial can be written as 1/2 k x final squared minus 1/2 k x initial squared. Then you see that in general, potential energy of spring is equal to 1/2 k x squared, where x is the distance from the equilibrium point. Okay, so if you compress or stretch a spring from its equilibrium point by x, then it has this much potential energy stored in it. And x is distance, equilibrium or relaxed position of the spring. That's when the spring is not stretched. So this is gravitational potential energy and spring potential energy. All right, so this is potential energy. The total potential energy that we have for a system is sum of these two, because we have only these two potential energies for now. Later on we talk about electricity. We have electric potential energy, but that's for the next course, that's electricity. But in here we have only these two potential energy. In general, we say the total potential energy is potential energy to the gravity plus potential energy to spring. You can add both of them together and call it potential energy in general. All right. Now, I want to go back to work energy theorem. We said that net work on an object is equal to change of its kinetic energy, delta K, which is K final minus K initial, right? But this net work is the net work done by all the forces. I would like to separate these forces. Some of them are conservative forces, some of them are non-conservative forces. So I write W of conservative plus W of non-conservative equal to delta K. But W conservative is either W of a spring or W of gravity, right? And W of any of those is negative change of potential energy, right? So instead of W of conservative forces, I put negative delta U potential, right? And then we have W non-conservative equals to delta K. Now I can write these as initial and final, right? This is negative U final minus U initial. That's what delta is, right? Always final minus initial. Plus W non-conservative equal to K final minus K initial. I want to move everything that has negative sign to the other side, so everything becomes positive. So get Ki plus Ui plus W non-conservative equal to Kf plus Uf. And that is called equation of conservation of energy. So instead of using the work of conservative forces, we use potential energy due to conservative forces. And those are the two conservative forces that we have. U is sum of these two. Some of it, if you have a spring, there is some contribution of the spring potential energy in there. If you have force of gravity, then there is some contribution of that. And these non-conservative forces are work of all the forces. Can be applied force, can be tension force, can be friction especially. And work of friction is usually negative. And that's usually only work of friction, because in most cases normal force doesn't do any work. If you move on a surface, the normal force is perpendicular to the direction of motion. It doesn't do any work. Tension force, if something's swinging on a rope or something, the tension force doesn't do any work. This is the total mechanical energy, they call it. The K plus U is called total mechanical energy of a system. Sum of the potential energy and kinetic energy. And then if you don't have any non-conservative forces working in the problem, there may be non-conservative forces. If the work of non-conservative force is zero, like WNC is zero, then you have initial mechanical energy is equal to final mechanical energy. That's called conservation of energy. W non-conservative equal to 0, then it's called conservation of energy. This is the more general conservation of energy that includes non-conservative forces.
How do you calculate the work of friction?
Work of friction, very good question. How do we calculate work of friction? It is easy if you have force of friction, because force of friction is always opposite the motion. If you have the force of friction, then you have displacement over a certain surface. Let's say you go from here to here, and this is the object. This will be the displacement, and the force of friction is this way. Then work of friction, which is usually the only non-conservative force that's working, is equal to magnitude of d times magnitude of fk times cosine of the angle between them.
Which is 180.
Cosine of 180 is?
0. Or no, negative 1. Sorry.
Negative 1. So it becomes negative fk times distance, if fk is constant. All right? So this is our main equation in this chapter. This solves every problem. You just need to use an initial and a final. So you need to draw two pictures, one with initial situation, one with final situation. Decide how much kinetic energy we have for each case, how much potential energy we have, if there is any work of non-conservative forces, and put everything in that equation. That gives you an equation to solve for one unknown. That's usually the way things work. Every problem that I did in the previous part with the work energy, now we can do it with this. Instead of using work, we use potential energy. Right? For example, if you have a bowl like this, hemispherical bowl, and you put a little piece of ice here, it slides to this point. You want to see how fast it's going at this point. And this has radius r, right? It's a hemisphere of radius r. So in order to solve this, you take this initial, this final, to make clear what we're looking for. What do we know about this initial situation?
Is VI 0?
VI is 0 because it starts from rest. Right? And V final is what we're looking for. Of course, there's force of gravity, right? In order to measure potential energy, we need to have a y-axis. Because potential energy is mgy. There's no meaning if you don't have y. So you have to set up a coordinate axis. And that's up to you, where you want to put the y equal to 0, and it has to be upward. So where would you like to start? Where is your 0 level?
The bottom of that circle.
You can put the bottom. Usually the lowest point of the problem, you put y equal to 0, because then all the values of y are positive or 0, right? That's easiest. So we put from here, let me put it right at the center. From here, you put the y-axis upward. That's to show that it's 0 level here. We put x-axis here, right? This x-axis just shows where y equal to 0 is, right? And then, what is the y at this point? You say this is a hemisphere, we said. Actually, it should be from the center, or what is the height of this point? If it is a hemisphere.
Just the radius.
From here to here, yeah, it's radius, right? Here is also r. Right? So, y initial is r. What is y final? 0. And is there any non-conservative force acting on it along this path? Yes, there is. There's normal force, right? Normal force is acting on that. but it's always perpendicular to the direction of motion. So normal force doesn't do any work. And there's no friction. So the work of non-conservative forces is equal to 0. Right? Then we can use this, Ki plus Ui equal to Kf plus Uf. And is any of these 0?
Ki
Ki is 0 because initially the speed is 0.
and Uf.
Uf is 0 because Yf is 0. U is mgy. So initial potential energy should be equal to final kinetic energy. Right? Kinetic energy, yes, mgr, which is initial, y, should be equal to 1/2 mv final squared. And what happens to m? M cancels, the mass doesn't matter. So V final is 2gr. So V final, the speed is square root of 2gr. Okay.